about blinded adaptations, permutation tests, and t-tests. This is joint work with Eckhard Glimm and Martin Posch, which it just appeared online in Statistics in Medicine, but also I'm going to include a little bit, a small, very small amount from this 2012 paper as well. So let me just start with the fact that clinical trials are premeditated. Everything about them, you pre-specify so many things, whether it's a superiority or a non-inferiority study, the population through the inclusion-exclusion criteria, the primary endpoint, secondary endpoints, the analysis methods, and the sample size and power. And so anytime you make a change after seeing data, that is rightly questioned, and people want to know, are they trying to gain an unfair advantage? And examples of trying to gain an unfair advantage might be changing the primary endpoint because you see that a different endpoint has a bigger treatment effect, or increasing the sample size even though you're at the end of the scheduled trial and you just decide, well, the p-value is very close, so let's just take a few more observations. Changing the primary analysis because the assumptions underlying that analysis are not met, that really bothers me because to me that's a very avoidable problem. You just do, your primary analysis should be something that doesn't require many assumptions, then you won't run into that problem. Changing the population because you see that there might be a particular subgroup that's doing quite well. So these would be attempts to gain an advantage. And you might say, well, what's the harm? I mean, after all, 0.05 is arbitrary anyway. But of course, if you're allowed unlimited freedom to change whatever you want, the actual type 1 error rate could be very large. And it's sort of reminiscent about this debate about the Bible code. This goes back hundreds of years. In fact, Sir Isaac Newton was a believer that, if you skip letters in the Old Testament, so you take, say, every 50th letter or every 100th letter, most of the time, of course, what you get, it doesn't spell anything when you take every 100th letter. But then once in a while, by chance alone, it does spell out things, and you can in fact find Bin Laden and Twin Towers. I forget how many letters you have to skip before you see that. But you have so many degrees of freedom because you're allowed to choose any number of letters to skip, and then of course, you go through a huge book like the Old Testament. And you're going to find sometimes when there seems to be a message, and critics have argued that this is just the play of chance. Brendan McKay at Australian National University says you can see the same thing in other large books, and he showed that using the book Moby Dick. So if you're allowed unlimited freedom to a lot of degrees of freedom, you can find some very unusual things. But changes made before you break the treatment blind are different, and that's because under the strong null hypothesis that treatment has no effect, then the blinded data should not be giving you any information about the treatment effect. And in fact, even if you think it feels like cheating, it's not really cheating. So for example, suppose you look at the blinded data and you see a bimodal distribution, and then you think, oh, this is not fair. I really know which group is the treatment group and which is the control. You don't know that if the strong null hypothesis is true, because if the null hypothesis is true, that bimodality should not be caused by the fact that one group got treatment and the other group didn't. Still, so the next thing I want to talk about then is permutation tests, which are very useful because they already condition on all the data other than the treatment labels. So if you let D be the data and Z be the treatment indicators, I'm using actually +1 and -1 for treatment and control. Under that strong null hypothesis, Z is independent of D. So there are a couple of ways of looking at that. One way to look at that is, hey, those observed data are what you would have seen regardless of what the treatments had been under the strong null hypothesis. You would have seen that data no matter what the treatments had been, no matter who got treatment and who got control. Another way to think about it is it's as if we observed the data and then we did the randomization. Then we randomly assigned people. If the strong null hypothesis is true, it should be like doing that. So peeking at that data doesn't change anything because remember the permutation test is already conditioning on that data as long as you don't look at the treatment labels. So the conditional distribution of your test statistic, which is a function of your observations and the treatment indicators, when you condition on all of the data, that's just the same as the distribution of T of capital Z little y. It's as if we're fixing little y at the observed value and then looking over the distribution of Z, where of course the distribution of Z depends on what kind of randomization you used. You could use simple, you might have used simple randomization or permuted block randomization or any number of other strategies. So here's an example with, small example with 4 different blocks. So this is permuted block randomization where within each block of 4, there are exactly 2 treatments and 2 controls. And those are the data up there at the top. And so you get the average treatment minus control difference in each of the blocks, and they're shown right there, those 4 numbers. And then the overall treatment minus control difference is the average of those 4 block means, which is 2.5. And so to get the permutation distribution, you're going to use the same method of randomization. So we're just going to scramble the treatment and control labels within each of those blocks. So each time you scramble them, I just change the labels, that changes the treatment minus control difference, and then of course that also changes the overall treatment minus control difference. And so you could do that thousands of times, or in a small example like this, of course you could exhaust all the possibilities, and when you do that, you get this nice permutation distribution, which is centered at 0, and then you look at your observed value, which is that blue dot there, at 2.5, and if you wanted to compute a one-tailed p-value, that would just be the area of the bars to the right and including 2.5. All right, so let's talk a little bit about blinded 2-stage adaptive procedures, because I'm going to tie these together in a little bit. So these are procedures that where you have 2 stages. In the first stage, you are allowed to look at the data and make some design change based on the blinded data, so you're not seeing the treatment labels. And the classic example would be to change the sample size, and those methods go way back to 1992 at least with Gould and Shi. But you could even do something more drastic. Of course, the fact that you can do something more drastic doesn't mean you should do it. But you could even change the primary endpoint on the basis of the first stage data. The previous argument about the fact that the permutation test already conditions on all the data shows that a permutation test on that first stage data is still valid. Now you do have to be a little bit careful because it is possible to make some subtle errors. So for example, you might want to do some adaptive analysis of covariance where you have a whole bunch of covariates and you want to pick the best covariate to include, and you want to just include one covariate and the treatment effect. So you could, you could think maybe I could do it one of two different ways. I could look at the ANCOVAs where I include, a single covariate, so I go through each covariate separately, and I pick the one that minimizes the mean square error in that model where you include treatment effect and the covariate. And then once I find the best covariate, then I could do a permutation test on the winner. Method two is to, I shouldn't really say ANCOVAs, I should say from regressions, leave out the treatment indicator and just regress y against each of the covariates separately, pick the covariate that minimizes the mean square error, now do a permutation test using the winning covariate. And so you might think that either of these is valid, but in fact, and maybe you don't think that if you're used to doing permutation tests, but this first method is not valid because in order to do that first method, you have to see the treatment labels to do that because you're including Z, the treatment indicators, in that regression. So that would not be a valid method of doing this adaptive regression. The other thing that you have to be careful about is you have to understand that you're really testing a strong null hypothesis when you do a permutation test. And so you can get into situations where it seems like everything should work out and it doesn't work out, and you're wondering, well, why didn't that work out? So here's a concrete example where what we're going to do is look at, we have two possible primary endpoints, and let's say, diastolic and systolic blood pressure, say, which actually we were confronted with this a long time ago in the DASH trial. We were trying to figure out which one of those to use. We did not do an adaptive procedure to pick which one to use, but let's suppose you did this. You're trying to figure out which endpoint to declare as the primary. You are not going to look at the treatment labels, but you're going to look at a covariate and each of the two endpoints. And remember, so this is blinded to treatment, except that the covariate is the amount of study drug in your blood. Okay, so obviously, even though you didn't physically look at the treatment labels, you essentially did by looking at a covariate that is going to completely unblind. So if you're allowed to do that, then you're going to completely unblind yourself. Then you could actually look at the z-scores for each of the two primary endpoints, and you could pick the one that has a bigger z-score. And clearly that has to inflate the type 1 error rate. So that is not a valid procedure. So you say, well, what went wrong here? Actually, nothing went wrong. Nothing went wrong. Because remember, you're testing the strong null hypothesis that treatment doesn't have an effect on anything. Did you?
I have a question. I think maybe I missed something. So
Yeah.
I understand how you could get the permutation distribution on blinded data.
Right.
How do you do the actual test? If you're talking about doing the test, how can you calculate the test statistic without unblinding?
Yeah, so at the end, what you're going to do is, what we're going to do is we're going to make an adaptation based on this blinded data, and then we're going to change something in the second stage. Then at the end, we do have to break the blind to analyze that, because we have to know what our observed value is and then get its permutation distribution. So what went wrong here, though, is that in a sense, nothing went wrong because you're testing the strong null hypothesis that treatment has no effect. So you are correctly rejecting that strong null hypothesis. You're saying treatment does have an effect, but the proper conclusion is that treatment has an effect on something that you looked at. Well, you already knew that before you started, right? You know that treatment is going to have an effect on the amount of study drug in your blood. So really, in a sense, nothing went wrong. It's just that you're only allowed to make a meaningless conclusion, and that's what you deserve, basically, for looking at a variable that completely unblinds you. So there's actually no error in thinking on that. It's just you have to keep in mind what you are allowed to claim. Now, I'm going to go out on a limb a little bit. This is, these statements have not been evaluated by the FDA, as they say on TV, or not been evaluated by my co-authors. My co-authors, tend to be pretty conservative, and it's a good thing, too, because sometimes I, come up with something crazy, and they say, no, that can't work. But I'm going to claim that this works. I really believe that you could go this far. I don't recommend this, but you could go this far. You could actually look at the first stage data, then decide what test statistic you're going to use. Remember, you don't have the treatment labels. And so by first stage data, I really mean the Ys. So you look at the first stage, the Ys, and you decide what test statistics. So you could say, I'm going to do a t-test, or I'm going to do a Wilcoxon test. And you also decide how much data to collect in the second stage. Then, after observing the second stage data, then you decide what test statistic you're going to use on the second stage and the method of combining those two test statistics. And I claim that the conditional distribution of that combination of test statistics, given the data, given the Y1 and Y2, is still its stratified permutation distribution, and so you could still get a valid null hypothesis by using the stratified permutation test. That, I claim, is going to control the conditional type 1 error rate and therefore the unconditional type 1 error rate as well. So, but for the rest of the talk, what I want to focus on is the fact that permutation tests are asymptotically equivalent to t-tests. We know this. And that suggests that if we have a valid permutation test in an adaptive setting, maybe we can deduce a valid t-test in an adaptive setting. So I'm going to consider the connections between permutation and t-tests and try and deduce the validity of adaptive t-tests from the validity of adaptive permutation tests. And I'm going to start with the one sample case, and I think a good example might be some of these community randomized trials, which a lot of the community randomized trials pair match communities, and then they randomize one member of the pair to treatment and one to control. An example would be the COMMIT trial, which used a community intervention to try and help people quit smoking. And they had 11 matched pairs of communities. And so if we look at just the difference in the quit rates between the treatment and control communities, here's a hypothetical pair where 30% of the treatment community was able to quit and 25% of the control community. So if you look at the difference, treatment minus control, it's 0.05. And if you do a permutation test, that just corresponds to permuting labels within a pair. And when you switch those two treatment and control labels, that's just going to change the sign. So you get minus 0.05. So in general, when you permute labels in a paired setting, it only changes the sign of the difference. And so we can think then about the permutation test as conditioning on the absolute value of the difference, which I'm calling DI positive. And in that case, minus and positive DI positive are equally likely under the permutation distribution. So if we look at the permutation distribution of the sum of the differences, that's just the distribution of the sum of the ZI times little di plus. Remember, we're conditioning on the absolute value of the difference, that is little di plus. The only thing that is random here are the Z's, which are -1 or +1 with probability 1/2. And in the first stage, we're going to make some adaptation on the basis of looking at the absolute values of those differences. So we're not breaking the blind, we're just looking at the absolute values. And then we're going to make some change in the second stage on the basis of that first stage decision. And the question is, what's the conditional distribution of the first stage sum given those absolute values and the adaptation that you made? And so I'm claiming that it's just the permutation distribution of that first stage sum, because the adaptation that you make is just a function of those absolute values of the D's. So conditioning on that change doesn't condition on anything more than you already were doing with the permutation test. So the null distribution of the sum of the DI's from the first stage, given those absolute values, is its permutation distribution. And so a permutation test on that first stage data is still valid. Now let's look at the mean and the variance of the permutation distribution. So the mean of summation of Zi, Di plus, well, remember the Di plus are just fixed constants, so we go inside the sum, and that's just Di plus times the expected value of Zi, which is 0. And the variance, we just square the Di plus gets squared, so we get Di squared, sum of Di squared times the variance of Zi. Variance of Zi is just its squared expectation because it has mean 0. And Zi squared, remember I'm using plus or minus 1 to indicate treatment and control, so Zi squared is just 1. So we get the sum of the Di squareds for the variance of that permutation distribution. And we know that the permutation distribution for large sample size is approximately normal with that mean and variance, and that you can deduce that easily from the Lindenberg-Feller central limit theorem that it will be approximately normal with that mean and variance. So in other words, what we're saying then is the conditional distribution of the sum of that first stage data, given the absolute values of the D's, asymptotically that's normal with mean 0 and this variance, the sum of the Di squareds. So this conditional distribution depends on the absolute values of the D's only through the sum of the squares of the D's. So if we divide by the square root of the sum of the D's, sum of the squares of the D's, and we look at the permutation of that thing, then the numerator is asymptotically normal with mean 0 and variance sum of the Di squareds. Denominator is the root of sum of little Di squareds. That's going to be asymptotically normal 0, 1. And this t statistic that I'm using here is very closely related to the usual t statistic. It's slightly different. So this t statistic here, we're using a slightly different variance estimator, S0 squared, where instead of the usual sample variance, we're using 1 over n times the sum of the Di squared, which is just the squared length of the D vector divided by n, the number of pairs. So this is very closely related to the usual t statistic. It's a little bit different. And so just recapping then, the permutation distribution of this slightly different t statistic is the conditional distribution of that statistic given the absolute values, and asymptotically that's the same as the conditional distribution of that t statistic given the sum of the Di squareds, and we showed that that was approximately standard normal. In other words, the conditional distribution of that, given the sum of the Di squareds, doesn't depend on the sum of the Di squareds. It's normal 0, 1. There's no sum of Di squareds there. And what that tells us is T prime has to be asymptotically independent of the sum of the Di squareds, because the conditional distribution of T prime, given the sum of the Di squareds, doesn't depend on the sum of the Di squareds. And that begs the question, is this true for all sample sizes if you make a normality assumption? So the question then is, if the differences are IID, and we're willing to assume that they're normal with mean zero under the null hypothesis, mean zero and variance sigma squared, can it be possible that the sum of the d's divided by the square root of the sum of the di squared, can that really be independent of the sum of the di squareds? And you look at that and you say, that's nuts. How could it be independent? Look, it's got the sum of the di squareds right there in the denominator. Can't be independent of the sum of the di squared, but actually it is independent. And one way to see that uses Basu's theorem. I was fortunate enough when I was at Florida State to have Basu as a professor. He was at Florida State, and I learned a tremendous amount from him, but he has a beautiful theorem. Recall that S is said to be a sufficient statistic for a parameter if the distribution of all the data, given that statistic, given that sufficient statistic, does not depend on the parameter. And it's complete if the expected value of a function of S being zero for all values of theta implies that that function is zero with probability 1. And that's, these two things are very important if you're trying to find the minimum variance unbiased estimator, because you really should look only at sufficient statistics, and then if the sufficient statistic is complete, that means you can only find one function of the sufficient statistic that is unbiased. So it's helpful in that area, among others. And then you have A is an ancillary statistic, means that its distribution doesn't depend on theta. And so really a complete sufficient statistic sort of summarizes all the information about the parameter, and an ancillary statistic is at the complete opposite end of the spectrum. It has nothing to do with the parameter, and Basu's theorem says that if you have a complete sufficient statistic and an ancillary statistic, those have to be independent. It's a beautiful theorem. So let's return to our setting where we have these differences that are normal with mean zero and variance sigma squared, and sigma squared is the parameter. That's the unknown here. Then it can be shown that the sum of the di squareds is complete and sufficient statistic for sigma squared. And I claim that T prime, that sort of strange looking T statistic, is ancillary because if you divide all the d's by sigma, they just cancel out in the numerator and denominator. It doesn't change anything. So T prime is an ancillary statistic, and so by Basu's theorem, T prime and the sum of the di squareds are independent. So that crazy looking theorem is in fact true. And in fact, the same argument can be used with the usual T statistic. We don't have to use the funny looking T statistic. So under the null hypothesis, that we have IID observations with mean zero and variance sigma squared unknown, the sum of the di squared, as I said, is complete and sufficient, and the usual T statistic is also ancillary for the same reason as before. If you divide all the d's by sigma, it doesn't change that T statistic. So by Basu's theorem again, the ordinary T statistic and the sum of the di squareds are independent. This is actually, this is in Xiao's book on mathematical statistics. So why is any of that important? It's important in adaptive sample size calculations for the following reason. So here's what you're going to do. Before the study starts, you're going to compute the sample size that you need. And then what you're going to do is, after you collect half of those observations, say, you are going to look at the data from the first stage, and you're going to look at the sum of the di squareds, which again is akin to a variance estimate of sorts. And then you're going to make a decision, okay, how much do I need to increase the sample size because the variance is bigger than I thought it was going to be? Well, Once we condition on the sum of the DI squareds from that first stage, then I've just argued that that T statistic from the first stage is independent of the sum of the DI squareds. So its conditional distribution given the sum of the DI squareds is exactly a T statistic with N1 minus 1 degrees of freedom. And then once we condition on the sum of the DI squareds, that fixes the second stage sample size. So then the test statistic on the second stage has an exact T distribution with N2 minus 1 degrees of freedom and is independent of that first stage T statistic. And so therefore, if we look at the p-values from using those T distributions, those will be independent uniforms under the null hypothesis. And so we can combine those by using the inverse normal method of combining p-values. So we take square root of n1 times phi inverse of the first stage p-value plus square root of n2 phi inverse of the second stage p-value divided by root n1 plus n2, and that will have an exact normal distribution given the sum of the DI squareds under the null hypothesis. And so if we reject if that combination is bigger than the upper alpha point of a standard normal distribution, then we know that conditioned on the sum of the DI squareds, the type 1 error rate is preserved at level alpha, and therefore the unconditional type 1 error rate is also preserved at level alpha. So this gives you a very reasonable two-stage procedure whose type 1 error rate is exactly alpha. There's no inflation whatsoever. Most other two-stage procedures are only approximate, whereas this is an exact one. Yes? Right. That's right. So given the sum of the DI squareds, now we have the second stage sample size is now fixed, right? Because it was just a function of the sum of the DI squareds. So now we have the first stage data, which we know has a T distribution because of that argument with the previous argument with sufficient statistic. Then once we condition on the sum of the DI squareds, that second set of data is a completely separate block of N2 observations. So the T statistic on that data, so that T2 is the T statistic using only that data. That will be independent of the first stage T statistic. Okay. Yes?
How does this differ from treating the two halves as two kind of separate clinical trials? It seems like you're analyzing them independently.
Well, yes, that's right. But you know, that same statement could be made about the usual thing that we do. You know, it also can be viewed as combining two independent groups of data. So it's really not different from that. But the advantage is that you're allowed to change the sample size based on that sum of the DI squared. So that's how you would do it in a one-stage setting. Now, I claim that you could make other adaptations too, such as actually changing the primary endpoint. Although, you know, I don't recommend that. I don't think that's a good idea. And to make that valid, you have to make some additional assumptions. Namely, you have to assume that your data are multivariate normal and the covariance matrix does not depend on the mean. In
the unblinded setting,
right.
you do something very similar also in terms of combining data from the first and second stage. Is this what's different here? Is it that here you're using the actual sample sizes of the two stages, whereas in the unblinded setting you're using sort of pre-specified weights?
Well, so in the unblinding setting, yeah, there are ways of combining them. But they are not going to have as much power as this is going to have. I mean, this is basically going to be as if you, had intended that sample size all along, because that combination of inverse p-values is going to be incredibly close to the usual fixed sample t statistic on n1 plus n2 observations. And that's not quite true if you're going to look at the treatment effect and then make a change based on the treatment effect. And the methods, I mean, you could, I think that, the main difference, I mean, apart from the nice feature that we don't like to unblind anyway because there's so many other advantages of maintaining the blind, but this will basically give you the same power as if you had a fixed sample t statistic the whole time. So I think that's that's a big advantage.
But I think the thing that Sarah's just saying is that if you look at the form of your test statistic,
Right.
it has almost the exact same form as another method. I was actually going to try to look it up because I think it's on my computer.
Right.
Where the second sample is fixed a priori at the beginning of the study. So
Right.
instead of using the N2 that you actually calculated,
Yeah.
you use, let's say for example, N1 equal to N2, and that's
Right.
where the power is used.
Right, but if you're going to do that, so if you're going to use the combination that would correspond to equal N1 and N2, regardless of whether you do have equal N1 and N2, that is definitely going to lose power if you drastically change N2. That will not happen here.
Right.
Yeah, because you're
You've increased N2 by that function.
right, and you've appropriately weighted that data instead of using equal weights on those two stages, because I'm taking notice,
But that function is not dependent on the actual test statistic. The new sample size is not dependent on the actual statistic, right? It's dependent on the
well,
squares.
but see here, you're taking square root of n1 times that inverse of the first stage p-value plus square root of n2. This is the new n2. So you're weighting the same way you would weight in a trial with those fixed sample sizes with a much bigger second stage sample size. Yeah.
What I mean is that function, N2 of sum of these squares,
Mm-hmm.
is that a good function for getting the new sample size?
Oh, I see, yeah. So that's a good question. So if there's a huge treatment effect, then that's not so good, right? Because that sum of the d squareds will also be big if you have a huge treatment effect. So, but I would argue, the number of clinical trials with a huge treatment effect, unfortunately, is relatively small. And so I think if you're close to the null hypothesis, which I would maintain we are in clinical trials often, that is going to be pretty darn close to the usual variance estimate. I mean, you have to have a very big treatment effect to have that far away from the usual variance estimate.
I guess it's because you're testing sigma squared rather than testing delta. Right?
Well, no, I mean, we're testing delta. That sigma squared was just an argument. That was an argument for showing why this is a valid procedure. We're still testing whether delta equals 0. That's our interest. That argument involving sigma squared was just to show why this is a valid procedure, arguing, in terms of that's independent of this first stage t statistic. Yes.
Sometimes when I get into the mathematical details, I lose the big picture. So,
Are you saying that's what's happening with me?
no, with me. So could you remind us again, what's the purpose of doing all the mathematics? So in the practical application in clinical trial, what's the goal? What's the problem trying to solve?
Okay, so this is a method for, before the trial starts, you don't necessarily have such a good estimate of the treatment effect, and I'm sorry, not the treatment effect, but of the variance. And so you are going to use this method to get a better estimate of the variance, and that's where you use the sum of the DI squared. So you're able to look at the data and deduce an estimate of the variance, and then change the sample size accordingly so you have good power to detect the given delta with this new estimate of the variance. Sorry, I should have made that more clear. Okay, yeah.
Let me ask you a different
Yeah.
question. I mean, this statistic is pretty, it's interesting. And let's say, for example, you had a lot of phase 2 data where you knew the distribution of the actual DIs. So phase 2 data, the DI, not the cap DIs, but the actual DIs.
Right.
And then you, in your phase 3, in a blinded manner, you can see the distribution of treatment effect, well, I shouldn't say treatment effect, but you could see that there were effects, things that were going beyond
Yeah.
what you had actually previously seen in an
Right.
phase 2 setting.
Right.
Is that information okay to look at?
I mean, it is okay to look at because under the null hypothesis that you should not be able to gain an advantage. And I've had people ask me that before. They say, hey, we think we have a really good idea what the variance is. So when we look at the absolute values of the Ds, we're actually going to see that there's a treatment effect because it's beyond, or the sum of the DI squares, because it's beyond what we would expect. But remember, under the null hypothesis, you should not be able to gain an advantage. That's only if the null hypothesis is false. So even that, which feels like it's cheating, is still a valid thing to do.
I think, a lot of these things are the same thing you talked about at the very beginning, or the intersection between what's okay to do statistically and
Right.
behavioral norms. And so people always hesitate to contravene behavioral norms, and it becomes tough for statisticians to try to
Right.
overcome a little bit of that resistance, especially when you're dealing with
But I would maintain that there's a long history of blinded, sample size re-estimation. So I would say that that's pretty much an accepted procedure, and guidance documents, by the FDA and the EMA, basically condone that. Although you do have to be a little bit careful, I think, because under the alternative hypothesis, some things can be going on. So anyway, so you can do the same sort of thing. You can do the same sort of thing in a 2-sample setting, and I'm not sure how much time I have because I guess I have unlimited time since he's not here. But you can do the same sort of thing in a 2-sample setting. Let's just assume for simplicity that the sample sizes are equal, then the numerator of the test statistic is just the difference between the sum of the treatment observations and the sum of the control observations, which I can write as the sum of Zi times Yi, where the Z's are plus or minus 1s. And we're trying to do the same thing. We're trying to get some more information about the common variance. We're assuming that the variance is the same between those two groups. And I'm sort of going to argue that based on the permutation test, we could also do an adaptive t-test. Permutation distribution is just the distribution of sum of Zi, Yi. Again, the Y's are fixed. Here it's slightly different because you also have the constraint, if you're conditioning on the sample sizes, that the sum of the Zi's is equal to 0. And if you compute the lumped variance, so this is just putting the two groups together and computing the variance of all those observations, it turns out that the mean and variance of that permutation distribution are 0 and that lumped variance, respectively. And so, again, you can use Basu's theorem to show that that 2-sample t statistic is independent of the lumped variance under the hypothesis of a common mean and the same variance in each group. And so what I'm saying is if you look at the lumped variance and then you make some sort of decision on the basis, you make a decision about increasing the sample size on the basis of that lumped variance, then the conditional distribution of the t statistic given the lumped variance, it still has a t distribution. You can do that very same kind of thing, a two-stage procedure. You look at the lump variance, you change the second stage sample size, then I'm saying conditioned on that lumped variance and under the null hypothesis, T1 and T2 are going to be exactly T with those degrees of freedom. You can compute those independent p-values from the first and second stage and then form that weighted combination, and that will be exactly standard normal under the null hypothesis, and this procedure will control the type 1 error rate both conditionally and unconditionally. So this is a valid method of looking at using that lumped variance as an estimator of the variance. Same issue applies, though, that you could say, well, is that really a good idea? The lumped variance should include the treatment effect as well. I'm taking the variance of all the observations. If treatment has a really big effect, then the control observations are on one side, treatment observations are on the other. That will really increase that lumped variance. But again, I maintain that in clinical trials, we're usually looking at small treatment effects, in which case that is a good estimator of the common variance. And so therefore, this will be a valid procedure, which will be an exact procedure, an adaptive t-test that exactly controls the type 1 error rate. So just in summary then, what I've tried to convey, perhaps poorly, is that permutation tests are often valid even in these adaptive settings as long as you maintain the blind, and there's a close connection between permutation tests and t-tests. And so therefore what we did was we deduced that certain adaptive t-tests are going to be valid, and we deduced that from the validity of adaptive permutation tests. So I'll stop right there. Thank you.
Yeah, there was some concern about the fact that this, when the null hypothesis is not true when you pull the variance.
Yeah.
But that'll end up in a bit of an illogical situation because your variance will overestimate the true variance. You'll end up with a much larger sample size than you need. So when there is a treatment effect, you end up with a larger sample size.
That's
which is counterintuitive.
No, that's absolutely right. But I continue to maintain that the size of treatment effects that are observed in our clinical trials are such that this lumped variance is an extremely accurate estimator of the variance, even in the presence of a treatment effect. Unless that treatment effect is just wildly huge, then you're absolutely right. Then you come to the conclusion, hey, my variance is huge, I need to really increase the sample size. And exactly the opposite is true because the treatment effect is causing that huge variance. So it is a theoretical possibility, but it just, as a practical matter, it just doesn't usually occur.
Michael, if we didn't have this methodology, what would we be doing? We would be just estimating the variance from
Right.
the first stage data,
Right. Right.
And then saying, well, based on this new estimate of variance, we're going to change the sample size.
Yeah. So, okay. So, all these people are practical. I'm not practical. See, I don't care about it. It's just like, no, seriously. You're right that if you just did what you normally might do, which is to say, I'm going to increase the sample size, I'm going to apply a regular t statistic at the end, pretending like I had that sample size all along, that will be approximately correct. It will not be exactly correct. It will give you approximately the correct type 1 error rate, and it'll be very close. This is just a method of making it be exactly alpha instead of approximately alpha. You know, when we worked on this, you know, I was sort of half joking a little while ago because I found this to be really pretty, this connection between permutation tests and t-tests, and the fact that you could deduce results. Of course, you still have to prove them, but from the permutation test. So I thought that was kind of an interesting, you know, connection. You know, to me, the fact that you can get almost as good a procedure just by doing the naive thing doesn't really bother me because I still like the, you know, that connection between them. But you're right that, you know, you could do this naive thing and almost always it's going to be just fine. It's going to have almost the right type 1 error rate. The inflation, if there is any inflation, is going to be very tiny.
Would it be possible, I'm sorry, was somebody else?
No, I don't think anyone else had their hand. Oh, no, she's just raising something. You didn't have a question, right? Okay. Oh.
There are settings, sort of non-inferiority or equivalence settings where blinded sample size or estimation inflates the type 1 error much more. There may not be so much of a concern in the superiority trial, but have you investigated some other settings?
No, you're right that I have been considering superiority studies here, and I am aware that there are papers in the non-inferiority setting where there can be a bit more of a problem. I frankly hate non-inferiority trials. I try and shy away from them whenever I can, but I recognize that sometimes they're unavoidable. But yeah, you're right. I'm focusing on superiority, not on non-inferiority. And the procedure, you know, some of these procedures that are approximately correct in the superiority setting may be a little bit less approximately correct in a non-inferiority setting.
Right, so I'd be curious to see how your procedure performs in the non-inferiority.
Right. Yeah. And that is interesting because really I'm assuming the null that they're equal. So, you know, you sort of reverse the roles of the null and alternative in non-inferiority. So I don't think it would necessarily work in a non-inferiority setting. Okay. Any other questions? All right. Well, thank you very much.